Have you ever wondered how engineers make sure that something really complex, like a plane's autopilot or a giant chemical reactor, won't just spiral out of control? I mean, how can they be so sure it won't, blow up? Well, the answer is all about a core concept in control systems called stability. And today, we're going to break down exactly how it works. The whole game here is about prediction, right? You can't just build a multi-billion-dollar satellite, launch it into orbit, and just kind of hope for the best. You need solid mathematical ways to prove that a system is going to behave predictably and safely once it's up and running. And that's the big question we're tackling today.
And the tools we use for this prediction are all built around control systems, just like the one you see here. Now, I know it might look a little abstract, but this basic loop, measure, compare, and correct, is basically the hidden brain inside tons of devices we rely on every single day.
All right, so here's our game plan. We're going to start with the single most important rule of stability. Then we'll dive into how engineers actually test for it, explore this really fascinating gray area called marginal stability, and then finally we'll tie it all together and see why this is just the bedrock of safe engineering. Okay, first up, the bounded input, bounded output rule, or as everyone calls it, BIBO. This is probably the most intuitive, common sense definition of what it really means for a system to be stable out in the real world. So to get BIBO, first we have to understand the word bounded. A signal, whether it's an input we're putting in or an output we're getting out, is bounded if it stays within a certain range. Think of it like a lane on the highway with guardrails. The signal can wiggle and move around, but it never ever goes above or below a fixed finite limit. And this slide right here shows the difference perfectly. On the left, you've got your bounded signals. A step function jumps to a value and just stays there. A sine wave oscillates forever, but it never goes higher than 1 or lower than -1. But on the right, whoa, that's a different story. You have a ramp function that just climbs and climbs to infinity and a growing exponential that just explodes upwards. So, with that in mind, here's the rule. A system is BIBO stable if you can absolutely guarantee that for any bounded input you give it, the output will also be bounded. You put a finite, well-behaved signal in, you get a finite, well-behaved signal out. That's the core promise of a stable system. But here's the catch, and it is a huge one. The rule applies to every single possible bounded input. If you can find just one solitary bounded input that somehow causes the output to fly off to infinity, the entire system is labeled unstable. The standard is absolute, no exceptions. Okay, so how do we actually test for this? I mean, we can't possibly try every single input, right? That would take forever. This brings us to our first real method, the impulse response test. You can think of a system's impulse response as its unique fingerprint. It tells you everything about its fundamental character. Now, the math here might look a little intimidating, but the idea behind it is actually pretty simple. What we're doing is measuring the total area or energy of this fingerprint over all of time. If that total energy adds up to a finite number, then you're golden. The system is stable. But if that energy just keeps adding up forever and ever towards infinity, the system is unstable. Simple as that. It gives us our first real mathematical guarantee. While that impulse test is powerful, there's an even more intuitive, even more visual way to see stability. And this is my favorite part. Welcome to the visual stability test, using a kind of map called the S-plane. This is a go-to tool for every control engineer out there. On this map, we plot these special points that define a system's behavior, and they're called poles. You can think of these poles as being like the system's DNA. They represent the natural ways the system wants to behave or vibrate. And believe it or not, their location on this map tells us everything we need to know about its stability. And here is the golden rule of the S-plane. If all of your system's poles are located in the left half of this map, the system is stable, period. This means any disturbance, any little poke, will naturally fade away over time. This is the safe zone. This is where you want to be. But if even a single one of those poles wanders over into the right half plane, where it has a positive real part, the system is unstable. Game over. The response will just grow and grow exponentially, blowing up over time. This is the danger zone. Any system with a pole here is just a disaster waiting to happen. So left is good, right is bad. Simple enough. But what happens if a pole isn't in the left and it isn't in the right, but it's sitting right on the fence, smack dab on that imaginary axis where the real part is exactly 0? Well, that's where things get really, really interesting. This brings us to a very special case, marginal stability.
This is what we call systems that are living right on the knife's edge between being stable and being unstable.
So, we call a system marginally stable when its poles are located directly on that central imaginary axis. They're not in the safe zone, but they're not quite in the immediate danger zone either. They are living life on the edge.
And if you look at how it behaves, the response doesn't die out like a stable system, but it doesn't explode like an unstable one either. It just settles into this sustained oscillation that goes on forever. So you might be thinking, hey, that looks bounded, right? What's the big deal?
The answer to why it's ultimately classified as unstable comes down to one critical, powerful word: resonance. This is the Achilles heel of a marginally stable system, and it's why it fails that strict Bibo definition we talked about.
Remember that every bounded input rule? Well, for a marginally stable system, there's a kryptonite. There's one specific bounded input that breaks everything. If you feed the system a sine wave at the exact same frequency as its poles on the axis, you get resonance. It's like pushing someone on a swing at just the right moment every single time. The pushes are small and bounded, but the swing goes higher, and in this case, the output grows with outbound, straight to infinity.
So let's bring this all together. Why have we been spending all this time talking about poles and planes and boundaries? Well, because in the world of engineering, stability isn't just some nice feature to have, it is the absolute foundation of safe design.
So let's recap the key rules of the road. First, the goal is always Bibo stability. A bounded input must always give you a bounded output. Second, the quick visual check. All of your poles have to be in the safe zone. That's the left half of the S-plane. And third, any pole on the imaginary axis or in the right half plane means your system is, for all practical purposes, unstable.
At the end of the day, checking for stability is always step one. It's the most critical thing you do. It's how we make sure a system is safe and predictable. But safety is just the beginning. Once we know for sure that a system won't blow up, the next, much more interesting question becomes, how do we make it fast? How do we make it efficient and precise? How do we design not just for safety, but for performance?